Today we're going to look at the quotient property of exponent rules. And a quotient, if we remember, is the solution to a division problem. So we are looking at what to do with exponents when we divide. So our rule is that when we simplify exponent problems with quotients, you are going to subtract exponents that have like bases. So here's an example. In this example, 9 to the 6th is being divided by 9 to the 2nd. And we know that it's being divided because it's in the form of a fraction, and a fraction bar always tells us to divide. When we're dividing and we have like bases, we take our exponents and subtract. So this has an exponent of 6, and this one has an exponent of 2. We would do 6 minus 2 to get an exponent of 4, and the base of 9 would stay the same. So why does this work? If we did 9 to the 6th divided by 9 to the 2nd, that would be 6 9s multiplied by each other in the numerator and 2 9s multiplied by each other in the denominator. What we know is that every time we have a 9 over a 9, that means 9 divided by 9, which is 1. Well, in this case, there are 2 sets of 9 over 9. They cancel each other out because if those make 1, then all I'm left with is 9 times 9 times 9 times 9. And then technically it's being multiplied by 1, but when you multiply by 1, your value stays the same. So what you're left with is 9 to the 4th power. So let's look at some examples. In this problem, we have x to the 7th divided by x to the 5th. You can always, just like with the product rule, you can write these out, expand them so that you can see them. So x to the 7th would mean 7 x's multiplied by each other. And then x to the 5th would be 5 x's. What happens is that every pair of x's will cancel each other out. And so what I'm doing is I'm canceling out 5 of those pairs, and what I'm left with are 2. So that means I'm left with x to the 2nd power. I could have also done that just by taking my exponent of 7 and my exponent of 5 and saying x to the 7 minus 5 power. And 7 minus 5 would give me 2. So x to the 2nd power would be my solution. In this problem, I have y to the 13th divided by y to the 5th. So I'm going to take my exponent of 13 and my exponent of 5, and I'm going to subtract. If I do 13 minus 5, I get 8. So that means that the solution to this is y, because my base stays the same, to the 8th power. For my next problem, I have 27k to the 10th divided by 9k to the 6th. In this problem, you'll notice I have a 27 and a 9. Well, they don't have the same base, but neither of them have exponents either. So just like when we were using the product rule, when we're using the quotient rule, if we don't have like bases, but they also don't have exponents, you're just going to divide like normal. So if I did 27 divided by 9, I would get 3. Then I can focus on my k's. These have the same base and they're being divided, which means I'm going to take the exponent of 10 and the exponent of 6, and I'm going to subtract. So I would do 10 minus 6, which would give me 4. My base of k needs to stay the same, so I'm putting this with my 3 that I got from doing 27 divided by 9. So now I have a base of k, and I found that my exponent would be 4. So this becomes 3k to the 4th power. For my next one, I have 6 into the 5th divided by 30 into the 3rd. Well, again, I have my whole numbers, so I have 6 and 30, but I know that I can't actually do 6 divided by 30 because that would give me a decimal, not a whole number. So what I can do instead is I can take this apart and look at it as if it were a fraction. So 6 over 30, And if I wanted to simplify that fraction, I know that a 6 will go into both of these. So I can divide the denominator and the numerator by 6. 6 divided by 6 would be 1, and 30 divided by 6 would be 5. So this is going to be 1/5. And then I can look at my n's. So now I have n to the 5th over n to the 3rd. They have the same base of n, so this is going to be n, and their exponents are different, so because I'm dividing, I'm actually going to subtract their exponents. 5 minus 3 gives me 2. So it's going to be 1/5 n to the 2nd power. For my next one, I have 42 f to the 8th g to the 6th over 6 f to the 5th g to the 7th. So I'm going to take this one at a time and focus on my whole numbers first. I have 42 over 6. Well, that means 42 divided by 6. And if I do 42 divided by 6, I get 7. Then I have my f's. I have f to the 8th divided by f to the 5th. I'm going to take my exponent of 8 and my exponent of 5, and I'm going to subtract. If I do 8 minus 5, I get 3. So this will have a base of f and an exponent of 3. Finally, I'm going to look at my g's. This has an exponent of 6, and this has an exponent of 7. If I do 6 minus 7, and you have to be careful here because in this case, I would do 6 minus 7, not 7 minus 6. It's always my numerator minus my denominator. So I would do 6 minus 7, and that would give me an exponent of -1. So my base would be g, and my exponent would be -1. Now, next week we're going to learn that we don't ever want to keep a negative exponent, but for right now, we would leave our answer just like this. For this problem, we have 12 over 32. Now, I know that if I do 12 over 32, that's going to give me a decimal answer. So instead of working with the decimal, I'm going to take this and I'm going to simplify this fraction. So if I look at 12 over 32, I know that a 4 can be divided into both of these. If I do 12 divided by 4, I get 3, and if I get 32 divided by 4, I get 8. So simplified, 12 over 32 simplifies to 3/8, and I'm just going to leave it like that. Now I can look at my variables. So I have c to the 9th over c to the 4th. I'm going to subtract my 9 minus 4 to give me 5. So that means I have a base of c and an exponent of 5. Then I have d to the 16th over d to the 3rd. I'm going to keep my base of d, and I'm going to do 16 minus 3, which gives me 13. So my solution is 3/8 c to the 5th, d to the 13th. For this problem, it looks similar, but it's a little bit different because what I notice about my numbers is that they have the same bases. Because they have the same bases, the same rule applies as with my exponents. I'm going to take my exponent of 5 and my exponent of 3, and I'm going to subtract. So if I do 5 minus 3, I get 2. That means this has a base of 4 and an exponent of 2. Now I can do the same thing with my variables. So I have a to the 2nd divided by a, and I know that even though I don't see an exponent here, there is an invisible 1. So I'm going to do 2 minus 1, which gives me a to the 1st power. Then I have b to the 6th over b to the 3rd. Again, I'm going to subtract my exponents, 6 minus 3, and I get b to the 3rd power. Now, if I look at my answer, I actually see that there's some simplifying I can do here. If I have 4 to the 2nd power, anything that's to the 2nd power can easily be changed. I know that 4 to the 2nd power actually means 4 times 4, and 4 times 4 is 16. So I can simplify that so that it says 16. Then if I look at a to the 1st, I know this is kind of like saying 1a. I don't need that 1 because that is invisible. So actually, I'm just going to get rid of it because there is an invisible 1 that I don't see if I just write A. Now, b to the third cannot have anything done to it because I don't know the value of b, and 3 can't be invisible. So I'm going to leave my answer just like this, 16ab to the third power. For this problem, I have bases of 5 because they have the same base. I'm going to subtract their exponents, so I have an exponent of 11 and an exponent of 4. If I do 11 minus 4, I get 7, so this is going to be a base of 5 raised to the 7th power. Then I'm going to look at d. So for d, I have an exponent of 9 over an exponent of 6, so I'll do 9 minus 6 to get 3. So this will be d to the third power. And for e, I'm going to look at my exponent of 4 and my invisible exponent of 1. I'll do 4 minus 1 to get 3, so this is e to the third power. Now, technically, I could multiply 5 by itself 7 times, but unless I have an exponent of 2 or 3, I'm usually just going to leave this the way that it is. So it's going to be 5 to the 7th, d to the third, e to the third. For this problem, I have 2 to the third over 2. They have the same base, the base of 2. This 2 in my denominator doesn't seem to have an exponent, but we all know that that means that there is an invisible exponent of 1. So I can do 3 minus 1 to get 2. So this is a base of 2 and an exponent of 2. Then I'm going to look at my a's. This also has an invisible exponent of 1. So I'm going to do 8 minus 1 to get a to the 7th. And then my b's. This b has an exponent of 4. My b in my denominator has an invisible exponent of 1. So 4 minus 1 gives me b to the third power. Again, I have an exponent of 2 here, so I can actually take this and I can simplify this. This 2 tells me to multiply the base by itself twice, so I'm going to do 2 times 2, which gives me 4. So I can simplify this to be 4a to the 7th, b to the third, and this is going to be my solution. And finally, we have 15r to the third s over 5r to the second. You'll notice the difference between these two problems is that in my first problem, my whole numbers had the same base. So I would subtract their exponents. In this problem, my whole numbers have different bases. But because they do not have exponents, I'm just going to go ahead and divide them. So I'll do 15 divided by 5, which gives me 3. Then I can deal with my exponents for my variables. So I have r to the third divided by r to the second. I'm going to do 3 minus 2, which gives me 1. So that's r to the first power. But again, I know that if it's to the first power, I don't actually have to write that. So I'm just going to leave it as r. Now, what you'll also notice is that we have this s. It does not have an s to be divided by in my denominator. What that means is that I am just going to rewrite my s so that it's right here. So my answer is 3rs.